In the mid-1950s, as the Cold War escalated, the Royal Air Force sought a new aircraft, leading to one of the most ambitious aviation projects in British history, the BAC TSR2. Designed to fly at supersonic speeds, carry a diverse array of weaponry, and operate from short, rough airfields, the TSR-2 would reposition Britain as a leader in aerial warfare. From its conception, the TSR-2 showcased British innovation, featuring advanced avionics for navigation and mission management, including an autopilot system for low-altitude, high-speed flights. However, the journey to its maiden flight was fraught with challenges: engine failures, bureaucratic infighting, and soaring costs. Despite its potential, the TSR-2 never reached full production, yet its legacy endures, captivating aviation enthusiasts and sparking debates about its capabilities. Some claim it was poised to break the Mach 2 barrier, pushing the boundaries of flight technology. But how close did this ambitious project truly come to revolutionizing aerial combat? In the early stages of the Cold War in the mid-1950s, the increasing sophistication of air defense systems led the Royal Air Force to consider a new aircraft to replace the English electric Canberra, which was becoming obsolete. As such, in the fall of 1957, the Ministry of Supply released General Operational Requirement 339, or GOR 339. This requirement was ambitious for the technology of the day, calling for an all-weather, long-range, low-level penetrator capable of delivering nuclear or conventional bombs with high-altitude, supersonic dash capability. It also needed to perform photo reconnaissance and electronic reconnaissance and operate from rough, short airfields. Simultaneously, around the world, similar aircraft were being developed, such as the American General Dynamics F-111 Aardvark and the Soviet Sukhoi Su-24. In the 1960s, the contract for the TSR-2 was awarded to an association of 3 companies: English Electric, Vickers Armstrong, and Bristol. This collaboration, which formed the British Aircraft Corporation (BAC), was notable for uniting former rivals. Despite early tensions, especially when Vickers Armstrong was named the prime contractor, the project moved forward, and BAC received a contract for 11 TSR-2 aircraft. Because it was being built by 2 companies, the first model's front half was designed and built by Vickers and the rear half by English Electric, which was located well over 200 miles apart. Despite the risky arrangement, when the 2 halves finally came together in March 1963, they miraculously fit perfectly. A total of 23 BAC TSR-2 strike and reconnaissance aircraft were made in various degrees of completion, with only a single finished model. The aircraft, which measured 89 feet in length, had a wingspan of 37 feet and enough space for a 2-person crew. It featured a tubular fuselage design with a pointy nose, painted in anti-flash white paint, a specific color designed to reflect the intense heat and light of a nuclear explosion, which was a detail common to nuclear bombers of the era. This model came with small shoulder-mounted delta wings, with downturned wingtips for stability at low speeds. The wings featured full-span leading-edge slats and trailing-edge flaps for optimal aerodynamic efficiency, supporting both high-speed performance and stable low-level flight. Additionally, a boundary layer control system used high-speed air from the engines blown over the wings to enhance lift and improve low-speed handling. Its true powerhouse came with the engines. A duo of cutting-edge Bristol Siddeley Olympus reheated turbojets that gave the TSR-2 exceptional thrust, enabling it to reach impressive speeds, especially for that time period. According to the flight envelope diagram, the aircraft could sustain a cruise speed of Mach 2.05 at altitudes between 37,000 and 51,000 feet, and even achieve a dash speed of Mach 2.35. The sleek aerodynamic profile of the TSR-2 was further enhanced by the strategic positioning of its air intakes within the fuselage. This model's versatility as a strike and reconnaissance platform was further emphasized by its substantial payload capacity. The internal weapons bay could accommodate up to 10,000 pounds of ordnance, while external hardpoints offered additional payload options. This flexibility allowed the TSR-2 to carry a wide array of weaponry, including both nuclear and conventional munitions. The cutting-edge design of the TSR-2 wasn't limited to its exterior. It also had advanced technology and systems that set it apart from its contemporaries. When finished, the BAC TSR-2 was to be equipped with some of the most advanced technology of its time. a pioneering fly-by-wire control system replaced traditional mechanical controls with electronic systems, significantly enhancing handling and responsiveness. Sophisticated electronic countermeasures (ECM), such as radar jammers and chaff dispensers, helped the aircraft evade enemy detection and missile systems. Advanced ejection seats designed to safely eject the crew at high speeds and altitudes were fitted in the TSR2, incorporating innovations that improved survival chances during emergencies. Furthermore, an automatic fuel transfer system maintained the aircraft's center of gravity as fuel was consumed, ensuring optimal balance and stability throughout the flight. Once in the skies, state-of-the-art avionics for navigation and mission management, including an innovative autopilot system that allowed for long-distance, low-altitude flights with reduced pilot workload, further distinguished this aircraft from its contemporaries. With these groundbreaking innovations, which were ahead of their time and have since become standard in modern military aircraft, the TSR2 was poised to re-energize Britain's weakened role as a world leader in aviation upon entering service. However, all this cutting-edge technology also made it extremely expensive, somewhat problematic, and the largest aircraft project in Britain to date. Throughout the TSR2's development, debates raged within the aviation industry and the Ministry of Defense about the future of bombers. Defense Minister Duncan Sandys argued for ballistic missiles over manned combat aircraft, while senior RAF officials believed the TSR-2 could be revolutionary, replacing the Canberra and the entire strategic bomber fleet. The program faced significant delays due to engine and landing gear issues. In February 1964, an engine exploded during a ground test, causing a 3-month delay for the first prototype. Pre-flight tests progressed slowly, with engineers working around the clock. With the 1964 election looming and the Labour Party, who opposed the program, poised for victory, the project faced political pressure. With this, the engineers turned to Roland B. Beeman, a highly decorated test pilot, to perform the first flight despite engine safety concerns. On September 27, 1964, Beamont prepared to take the TSR-2 prototype on its maiden flight from Boscombe Down, Amesbury, Wiltshire. The aircraft faced numerous technical issues, including the risk of engine failure and malfunctioning landing gear. Despite these challenges, Beamont did not hesitate, and the aircraft took to the sky. The engines held together as Beamont guided the aircraft through its first minutes of flight, completing 2 wide circuits at an altitude of 7,000 feet. Beamont was impressed by the aircraft's exceptional handling qualities. However, the fun was short-lived. As the TSR-2 touched down, a violent vibration in the landing gear, so powerful it made the pilot dizzy, nearly sending the aircraft out of control. Thankfully, the vibrations subsided and Beamont deployed the drag chute, bringing the TSR-2 to a safe stop. Though the flight lasted a mere 14 minutes, this maiden voyage was a significant milestone. Following the first flight of the BAC TSR2, the aircraft was grounded for engine replacements and landing gear repairs. During this maintenance period, a political storm unfolded. The new Labour government, led by Prime Minister Harold Wilson and Defence Minister Dennis Healey, won the election. Speculation arose that an unofficial deal was struck during a visit to the United States. Britain would cancel the TSR-2 in exchange for U.S. support for an $8.4 billion loan from the International Monetary Fund. This would push the Royal Air Force to adopt the American F-111 Aardvark instead. Despite the political turmoil, the TSR-2 flew again on December 31, 1964. However, it continued to face persistent vibrations and landing gear malfunctions. Yet there were moments of triumph. During Flight 14, the TSR-2 achieved Mach 1 on dry power alone, demonstrating its supercruise capability. Beamont then engaged a single reheat unit, outpacing the Chase English Electric Lightning, Britain's fastest aircraft, piloted by Wing Commander James "Jimmy" Dell. Dell later remarked that the TSR-2 handled like a big lightning. Over 6 months, the TSR-2 completed 24 test flights, with test pilots praising its basic flying qualities. However, the complex electronics were not yet fitted, and these achievements were not enough to save the program. On the morning of April 6, 1965, the second TSR-2 prototype was scheduled to make its maiden flight. However, before it did so, a faulty fuel pump needed replacement, prompting test pilot Jimmy Dell to take a lunch break at a nearby social club in Amesbury. As he sat in the club, a television tuned to the Chancellor of the Exchequer's annual budget speech delivered some shocking news. The TSR2 program was cancelled by the government. Dell rushed back to the airfield, but it was too late. Despite the aircraft being ready to take to the skies, the Air Ministry had already impounded it. BAC's plea for a limited test flight program for the two flyable prototypes was rejected by the Air Ministry, especially after the project's final price tag was revealed, an equivalent of $21.2 billion in 2024 dollars. By then, the mission for the TSR-2 had become obsolete as NATO shifted focus from nuclear Armageddon to measured responses to Warsaw Pact hostility. This change in strategy required aircraft with vastly different capabilities than the TSR-2, such as the multi-role F-4 Phantoms, low-level strike Blackburn Buccaneers, and versatile V-STOL Hawker Siddeley Harriers, all of which the Royal Air Force either already possessed or was developing at the time. In the aftermath of the cancellation, the RAF was left with only one plane that had flown several times, another that was on the verge of flying, and a handful of uncompleted production prototypes. The two finished aircraft were quickly scrapped or used as target practice, and all but two of the unfinished prototypes met the same fate, with some ending up as static displays in museums. Everything else associated with the project, tools, assembly facilities, plans, and design documents, was destroyed as if the TSR-2 had never existed. Countless people lost their jobs. Ironically, Britain also abandoned its plan to buy F-111 from the United States due to their escalating costs, which surpassed those of the TSR-2. It wasn't until 1980 that the RAF finally acquired an aircraft somewhat comparable to the TSR-2, the Panavia Tornado. Developed jointly by Britain, Germany, and Italy, the type became a mainstay of the Royal Air Force. Although never developed beyond the prototype stage, the BAC TSR2 remains one of the most controversial British combat aircraft designs in history. To this day, some continue to argue that its cancellation was a mistake bordering on treason, while others believe it was justified given the high cost of the project and the ever-changing strategic environment. Certain experts suggest that the true tragedy was not the TSR-2's cancellation, but that it hadn't been canceled years earlier, before so much money and effort had been wasted, believing that the aircraft should have remained flying as pure research vehicles, contributing to the British aerospace industry as a whole. Nearly 60 years later, conspiracy theories still surround the TSR-2's demise. Some speculate that Prime Minister Harold Wilson was secretly a communist and axed the project at the Soviets' behest, while others suggest that of sinister United States efforts to sabotage the TSR-2 program because it outclassed any aircraft they could ever build. According to aviation historian Frank Barnett Jones, quote, "There was little doubt that America would have a definite interest in seeing the British aviation industry reduced to such a level of ineffectiveness that it would be unable to continue in its present structure." The TSR-2's 14th flight, which achieved a Mach 1.2- and surpassed the Lightning aircraft chasing it, has contributed to its somewhat elusive and exaggerated reputation. However, retellings of this event often omit the fact that the Lightning pilot had shut down one of his two engines to conserve fuel and did not use afterburners. Still, because of this brief Mach 1.2-, the TSR-2, with advanced avionics and, most importantly, its powerful Bristol Siddeley Olympus reheated turbojet engines, has gone down in history as easily a Mach 2 aircraft, despite never having the opportunity to demonstrate its capabilities fully. However, the overall consensus is that the TSR-2 was simply too advanced for its time, a groundbreaking design that fell victim to a series of unfortunate political and economic circumstances. Screaming through the skies at an unprecedented 540 miles per hour, Germany's Messerschmitt Me 262 ripped through Allied fighters, outpacing them by more than 100 miles per hour. Its arsenal of 4 30mm cannons spat destruction, capable of ripping through the toughest bomber armor with terrifying ease, while its advanced engines allowed it to soar to altitudes where many Allied aircraft gasped for air. The Nazis may have been staring at impending defeat, but this airplane seemed like a sudden miracle from God, the first operational jet fighter. But from the perspective of Allied pilots, it was the devil's work. The appearance of these aircraft over Europe sent shockwaves through Allied ranks. Pilots spoke in hushed tones of phantom fighters that materialized from thin air, unleashed hell, and vanished into the clouds before anyone could react. As the Third Reich teetered on the brink of collapse, German leaders clung desperately to the hope that this cutting-edge creation might yet turn the tide. In the late 1930s, as Europe teetered on the brink of another world war, aircraft designers across the continent were pushing the boundaries of aviation technology. Piston-engine aircraft were approaching their physical limits, and engineers began to explore alternative forms of propulsion. In Germany, a young physicist named Hans von Ohain was working on a revolutionary new type of engine, the turbojet. Von Ohain's work caught the attention of Ernst Heinkel, one of Germany's leading aircraft manufacturers. Heinkel saw the potential of jet propulsion and began secretly developing a jet-powered aircraft. On August 27, 1939, just days before the outbreak of World War II, Heinkel's efforts bore fruit as the HE-178 became the world's first jet aircraft to fly. This breakthrough did not go unnoticed by the German Air Ministry. In 1940, spurred by the potential of jet propulsion and the weaknesses exposed in the Luftwaffe during the Battle of Britain, they issued a specification for a jet-powered fighter aircraft capable of speeds over 600 miles per hour. Among the German aircraft manufacturers who answered the Air Ministry's call was Messerschmitt AG, led by the brilliant but controversial designer Willy Messerschmitt. His team had already produced the Bf-109, one of the most successful fighter aircraft of the war. Even before the requirement was announced, Messerschmitt AG had already been working on their own concept for a jet-powered aircraft, known as Project 1065. This early design envisioned a conventional aircraft with straight wings and a single jet engine. Now, the company would need to evolve its design to meet the new specifications. By 1941, Messerschmitt's team had radically altered the aircraft's configuration. The design now incorporated 2 jet engines, one under each wing, offering increased thrust and improved reliability. This twin-engine layout also allowed for a slimmer fuselage profile, enhancing the aircraft's aerodynamics. These changes would give birth to the revolutionary first Me-262 prototype. The most striking feature of the first Me-262 was its swept wings, a design element that significantly reduced drag at high speeds. The wings incorporated an 18.5-degree sweep and were mounted midway up the fuselage. This sweep angle was carefully chosen as a compromise between high-speed performance and low-speed handling characteristics, essential for an aircraft expected to operate in various combat scenarios. The wings had a span of 41 feet 6 inches and a total area of 234 square feet, providing an aspect ratio of 7.32. This was considerably different from the straight wings of contemporary fighters like the Bf-109, which had an aspect ratio of 6. The aircraft's sleek aerodynamic fuselage measured 34 feet 9 inches in length, with a height of 11 feet 6 inches. Its pointed nose housed the cockpit and was designed to accommodate radar equipment in future versions. The pilot sat under a bubble canopy offering unparalleled 360-degree visibility, a crucial advantage for a fighter aircraft. This was a significant improvement over the more restricted view from the Bf-109's framed canopy. The cockpit boasted advanced features for its time. A gyro gun sight was incorporated to automatically calculate the lead necessary to hit a moving target, making the aircraft a potentially lethal opponent in air-to-air combat. The layout was designed for optimal pilot efficiency, with key instruments and controls placed within easy reach. The control stick was equipped with buttons for firing the guns and jettisoning the canopy in case of emergency. At the heart of the Me-262V1 were its Junkers Jumo 004 turbojet engines mounted in pods under the wings. Each engine was designed to produce 1,980 pounds of thrust, promising speeds of up to 540 miles per hour in level flight, a performance that would far outstrip any Allied fighter of the time. For comparison, the North American P-51 Mustang, one of the fastest Allied fighters, had a top speed of about 440 miles per hour. The Me-262's engines were fed by intakes on either side of the nose, with exhaust exiting at the rear of the engine pods. The intakes were carefully designed to slow down the incoming air to subsonic speeds before it entered the compressor, a crucial feature for efficient jet engine operation. The airframe made extensive use of aluminum alloys to save weight while maintaining structural integrity. The V1 prototype had an empty weight of approximately 8,400 pounds and a maximum takeoff weight of about 14,100 pounds. This gave it a power-to-weight ratio significantly better than any piston-engined fighter of the time, contributing to its exceptional performance. The Me-262's landing gear configuration was equally innovative. It featured a tricycle arrangement with a nose wheel and two main wheels retracting into the fuselage. The main gear retracted inward into the wing roots, while the nose gear retracted forward into the fuselage. This design, unusual for German fighters of the era, was chosen to provide improved visibility during takeoff and landing and enhance ground stability. The layout also kept the jet exhaust farther from the ground, reducing the risk of foreign object damage to the engines during takeoff and landing. The prototype carried four 30mm Mk108 cannons mounted in the nose. These powerful weapons were chosen for their ability to potentially destroy an Allied bomber with just a few well-placed hits. Each Mk108 had a rate of fire of about 650 rounds per minute, and the concentrated firepower of four such cannons was unprecedented in fighter aircraft of the time. Some versions were also designed to carry rockets under the wings, further increasing the aircraft's destructive potential. On April 18, 1941, the Me-262V1 prototype made its maiden flight at Augsburg Airfield. However, due to delays in jet engine development, this initial flight used a conventional Junkers Jumo 210 piston engine mounted in the nose, with two jet engines fitted in the wings for testing purposes only. The test pilot for this historic flight was Fritz Wendel, Messerschmitt's chief test pilot. It wasn't until July 18, 1942, that the Me-262V3 prototype made its first flight powered solely by jet engines, again with Wendel at the controls. While he reported that the aircraft handled well, he noted that it lacked power. This issue would be addressed in subsequent prototypes as more powerful versions of the Jumo 004 engine became available. The testing phase revealed several challenges. The revolutionary nature of jet propulsion presented unfamiliar problems to test pilots and engineers. One significant issue was the slow acceleration of the jet engines, which made takeoffs and landings particularly hazardous. The aircraft's high landing speed, much faster than that of piston engine fighters, led to the development of a drogue parachute system to aid deceleration during landing. High-speed testing revealed that the Me-262 could reach speeds approaching Mach 0.86. However, pilots encountered control difficulties as the aircraft neared the sound barrier. This led to further refinements, including strengthening of the airframe and improvements to the control surfaces. The testing process also exposed persistent issues with the Jumo 004 engines. They were prone to catching fire and had a short operational life, sometimes lasting only 10 hours before requiring an overhaul. Engineers worked tirelessly to improve the engines, but wartime shortages of high-quality materials meant many of these problems remained unresolved. Despite these challenges, the Me-262 progressed through its testing phase. The lessons learned during testing led to numerous refinements in the design. The wings were reinforced to handle the stresses of high-speed flight, and the control systems were modified to improve handling at transonic speeds. The cockpit layout was also refined based on pilot feedback to improve ergonomics and combat effectiveness. After extensive testing and refinement, the first production models of the Me-262 were delivered to the Luftwaffe in April 1944. These aircraft incorporated all the lessons learned during the prototyping and testing phases, resulting in a fighter that was faster and more heavily armed than anything the Allies had in service at the time. The Me-262 made its combat debut in July 1944, when a single aircraft successfully attacked a British Mosquito reconnaissance plane over Munich. This marked the beginning of a new era in aerial warfare as the world's first operational jet fighter entered the fray. The initial variant, the Me-262A-1A, served as the primary fighter, showcasing the aircraft's revolutionary capabilities. As August 1944 arrived, the Luftwaffe began deploying Me-262s in greater numbers. Simultaneously, Messerschmitt engineers worked to address early technical challenges, particularly focusing on improving the reliability of the UMO-004 engines. These efforts led to the later production of UMO-004B-4 engines, which gradually extended the operational life from a mere 10 to 25 hours to as much as 50 hours. In September, the Luftwaffe formed its first dedicated Me-262 unit, Kommando Nowotny, under the command of ace pilot Walter Nowotny. Despite the pilot's initial inexperience with jet combat, the unit's Me-262s quickly proved their worth. On October 7, 1944, they demonstrated their potential by shooting down 9 B-24 Liberators in a single engagement without suffering any losses. As combat experience grew, so did the Me-262's versatility. The Me-262A-1AU-3 reconnaissance variant emerged, replacing the nose-mounted guns with cameras for high-speed, high-altitude surveillance missions. This adaptation highlighted the aircraft's potential beyond air-to-air combat. The Me-262's superior speed made it a formidable opponent, allowing German pilots to dictate the terms of engagement. They developed effective tactics, approaching Allied formations in shallow dives, making lightning-fast attacks, and then zooming away before the enemy could react. However, the jets remained vulnerable during takeoff and landing, prompting some units to experiment with rocket-assisted takeoff systems to reduce this risk. By late 1944, the Luftwaffe introduced the Me-262A-2A variant, known as the Sturmvogel, Storm Bird. Optimized for the fighter-bomber role, it featured a strengthened undercarriage to handle increased weight and could carry 2 550-pound bombs under the nose. This adaptation reflected the changing demands of the war as Germany found itself increasingly on the defensive. As 1945 dawned, the Me-262 continued to evolve. Cockpit pressurization was introduced, allowing for more effective high-altitude operations above 26,000 feet. This improvement was crucial for intercepting high-flying Allied bombers and for conducting reconnaissance missions. Additionally, the Me-262B-1, a variant, addressed the need for pilot training by featuring a second cockpit for an instructor. In January 1945, the Luftwaffe formed a special unit, Jagdverband 44, under the command of Adolf Galland. Composed of Germany's most experienced fighter pilots, this elite unit achieved impressive results despite entering the war in its final months, further demonstrating the Me-262's capabilities in skilled hands. As the conflict neared its end, Messerschmitt continued pushing the aircraft's performance envelope. They developed the Me-262B, 1A U-1 night fighter, equipped with FUG-218 Neptune radar, its characteristic antenna array resembling stag's antlers. This variant enabled the interception of Allied bombers in darkness, adding a new dimension to the Me-262's combat capabilities. The final major variant, the Me-262C, was designed to incorporate a rocket engine in the tail for short bursts of extreme speed. Although this model didn't see combat, it represented the ongoing ambition to enhance the Me-262's performance even in the war's closing stages. Throughout its operational history, the Me-262 had a significant impact on Allied air operations. While fuel shortages and vulnerable airfields limited its availability, when operational it proved to be a potent weapon. German pilots claimed 542 Allied aircraft destroyed, although the actual number is debated. Even if lower, the psychological impact on Allied air crews was considerable. These continuous improvements and adaptations demonstrated the Me-262's vast potential, hinting at what might have been possible had the aircraft entered service earlier in the conflict. Despite its late introduction, the Me-262 left an indelible mark on aviation history, setting the stage for the jet age that would follow. Its swept-wing design and pod-mounted engines became standard features of jet aircraft for decades to come. The challenges encountered in its development and operation provided valuable lessons for future jet aircraft designers. After the war, captured Me-262s were extensively studied by the Allied powers. The Soviet Union's MiG-15 and the United States F-86 Sabre, both important fighters of the Korean War era, showed clear influences from the Me-262's design. Today, several Me-262s survive in museums around the world, including the National Air and Space Museum in Washington, D.C., and the German Museum of Technology in Berlin. In recent years, several flying replicas have been built, allowing a new generation to experience the sight and sound of this revolutionary aircraft. The Me-262 represents a pivotal moment in aviation history, marking the transition from the piston engine era to the jet age. Its legacy lives on in every modern jet aircraft, a testament to the ingenuity and foresight of its designers, even as it serves as a reminder of the technological advancements driven by the tragedy of war. The original McDonnell Douglas F-15 Eagle may rightfully be considered one of the most iconic and effective fighters of the 20th century. Yet the next generation F-15 short takeoff and landing maneuver technology demonstrator, ahead of its time when first launched in the late 1980s, set the stage for a brand new dawn in the next century. Soaring through the skies with extraordinary aerobatic finesse, this super-powered Eagle proudly showed off its pioneering design and next-level capabilities. By incorporating advanced thrust vectoring controls and canards, this futuristic flying machine could pull off daring aerial maneuvers, take off with incredibly low rotation speeds, and land on remarkably short runways. This was a leap forward from its predecessors and contemporaries. Even NASA made sure it got hold of the aircraft to test their most innovative new technologies. Thanks to the progress made by the revolutionary F-15 STOL MTD project, the world has borne witness to the development of a new generation of aircraft that have come to dominate the ever-changing face of modern warfare, such as the Lockheed Martin F-22 Raptor as well as the F-35 Lightning II. McDonnell Douglas began developing the original F-15 Eagle during the Vietnam War to meet the United States Air Force's need for a dedicated air superiority fighter to take on the Russian Mikoyan-Gurevich MiG planes used by communist North Vietnam in the tumultuous skies over Southeast Asia. Designed as an epitome of modern aviation technology, the F-15 program aimed to create a versatile, highly maneuverable aircraft with superior speed, agility, and firepower compared to existing fighters. Powered by twin Pratt and Whitney F-100 turbofan engines, the Eagle could achieve speeds exceeding Mach 2.5, enabling rapid deployment across vast operational ranges. Its agility was underscored by an impressive thrust-to-weight ratio, allowing for tight turns and complex aerobatic maneuvers. What's more, the F-15's durable airframe was built to endure the demands of intense aerial combat. Its armament consisted of AIM-7 Sparrow and AIM-9 Sidewinder missiles, alongside a 20mm M61 Vulcan cannon, establishing its dominance in air-to-air combat. Additionally, it was equipped with advanced radar systems, such as the AN/APG-63 and later the AN/APG-70, capable of identifying and engaging targets from great distances, and featured cutting-edge avionics and electronic warfare systems, such as the Tactical Electronic Warfare System, providing pilots with unparalleled situational awareness. Upon completion, the F-15 was introduced into service in 1976, just missing out on the chance to see combat in Vietnam. However, it would soon get the chance to prove its mettle on a different aerial battlefield when it was used by the Israeli Air Force to devastating effect in various Middle Eastern conflicts from the late 1970s onwards. In the early 1990s, the F-15 would shine during the Gulf War, where it accounted for 36 of the 39 air-to-air victories by the U.S. Air Force against Iraqi planes. It would also be incorporated into the Saudi Arabian and Japanese Air Forces, and has been credited with over 100 victories and 0 losses in aerial combat, making it one of the most successful fighters of all time. Yet rather than gunning enemies in vicious dogfights, one particular F-15 would find itself performing a very different, but no less important role. As Cold War tensions promoted fierce competition between the United States and the Soviet Union, both sides were constantly looking for ways to improve their aircraft to get the edge over rival planes as modern air combat evolved. While the original F-15 was clearly a highly capable fighter, American aeronautical engineers believed there was a way to make it even better. Aiming to push the boundaries of conventional aircraft performance, the goal was to equip the Eagle with advanced aerodynamic and propulsion systems that would enable short takeoff and landing or STOL capabilities and unprecedented control and stability. In 1975, the team at the Langley Research Center in Hampton, Virginia, began investigating thrust vectoring technology, which would alter the direction of an aircraft's engine thrust, giving the pilot greater control over pitch and yaw during flight. Having conducted sponsored programs to research two-dimensional thrust vectoring nozzles, Langley began working with McDonnell Douglas in 1977 to begin a system integration study of thrust vectoring, thrust reversing, and 2D nozzles on the F-15. It was believed that the fighter's robust, high-strength aluminum alloy airframe, which was 63 feet 9 inches long, 18 feet 6 inches tall, and had a wingspan of 42 feet 10 inches, could easily accommodate the necessary modifications, and that her 2 powerful Pratt and Whitney F100 turbofan engines would provide a good platform for integrating and testing the new nozzle designs. These could be vectored up to 20 degrees in any direction, providing incredible agility and enabling maneuvers previously thought impossible for a jet of its size. Another difference from the standard F-15 Eagle was the incorporation of canard control surfaces, already used to great effect since the 1960s, beginning with the groundbreaking Swedish Saab 37 vegan multi-role fighter, one of the most innovative aircraft of its time. Unlike traditional control surfaces, these small forward wings, which had a span of 26.5 feet and were positioned in front of the main wings, were actively controlled and could move independently. The canards would provide the aircraft with additional lift, increase airflow over the wings, and improve overall aerodynamic performance, even at low speeds, such as during takeoff and landing phases, reducing the runway length required for these operations. This would provide a tactical advantage by enabling operations from less prepared airfields closer to the front lines, or where conventional longer runways had been damaged or could not be used. Furthermore, the F-15 STOL MTD incorporated an Advanced Digital Flight Control System, or DFCS, which processed large amounts of data in real time and managed the complex interactions between conventional control surfaces, canards, and thrust vectoring nozzles, as these features significantly altered the aircraft's flight dynamics compared to the standard F-15. This DFCS was critical for achieving the desired performance enhancements and ensuring the aircraft's stability. In 1984, the Flight Dynamics Laboratory, the Air Force Aeronautical Systems Division, awarded a contract to McDonnell Douglas for an Advanced Development STOL MTD experimental aircraft. The The aircraft used for the project was the pre-production TF-15A No. 1. It had the USAF serial number 71-0290. This aircraft was an F-15B two-seat model initially designed for training, chosen to facilitate the testing and evaluation process, as it would allow for a test pilot and a flight engineer or test engineer to be on board during experimental flights. It was the sixth F-15 built by McDonnell Douglas, and was the first two-seater version out of two prototypes. With the prototype finally ready in 1988, testing began at Edwards Air Force Base in California, a central location for many of the United States Air Force's test and evaluation activities, especially for experimental and cutting-edge aerospace projects. It was here that Captain Chuck Yeager, flying a Bell X-1, famously broke the sound barrier for the first time, as well as providing the landing site for the first space shuttle mission. The base is known for its extensive facilities that support a wide range of flight test activities, including large dry lake beds that are used as natural runways for testing aircraft under various conditions. This made it an ideal location for assessing the STOL MTD's advanced short takeoff and landing capabilities, as well as its enhanced maneuverability features in a controlled but operationally relevant environment. The F-15 STOL MTD made its first flight on September 7, 1988, the first of approximately 200 flights, which would take place over the space of the next 3 years as it was carefully examined and evaluated by some of the USA's best aeronautical brains, who gained valuable insights about the effects of the aircraft's revolutionary technology. While its top speed of 1,522 miles per hour and service ceiling of 60,000 feet were unsurprisingly similar to the standard F-15, the differences were far more pronounced in the areas the STOL MTD was designed to test. Firstly, the STOL MTD proved capable of executing vectored takeoffs, impressively rotating at speeds as low as 36 knots or 42 miles per hour, a significant departure from conventional aircraft performance. This innovation contributed to a 25% reduction in the distance required for takeoff. Moreover, the F-15 STOL MTD could land on a mere 1,650 feet of runway, a fraction of the 7,500 feet needed for the standard F-15. In addition, the aircraft was equipped with the capability for thrust reversal in flight, allowing it to achieve rapid deceleration, demonstrating the advanced engineering and design principles that went into its development. Testing was deemed complete on August 15, 1991, meaning STOL MTD's job was done, and it was officially retired from the U.S. Air Force. However, it wouldn't be long before the state-of-the-art experimental plane was back in the air, and this time it would be in the service of another prestigious institution on the very vanguard of technological progress. After its initial phase of U.S. Air Force military testing had concluded, the F-15 STOL MTD was acquired by NASA. On June 15, 1993, it arrived at their Dryden Flight Research Center, also located in Edwards, California, now known as the Armstrong Flight Research Center, to begin an advanced research program. The project was named ACTIVE, an acronym for Advanced Control Technology for Integrated Vehicles. Their aim was to significantly advance the synergy between engines and aircraft, setting a new standard for the next wave of high-performance aerospace applications. This trailblazing initiative built upon the solid foundation of innovations from previous projects. Seeing the potential for further modifications, NASA experimented with the integration of pitch-yaw balance beam nozzles, which provided a full 360-degree arc for thrust redirection, a major advancement in thrust vectoring capabilities. As a result, the F-15 Active could execute post-stall maneuvers, high angle of attack operations, tail slide maneuvers, and tight and fast vector rolls. After the Active program concluded in 1999, the aircraft served as a versatile platform for testing various aerospace innovations. Between 1999 and 2008, it played a crucial role in evaluating the Intelligent Flight Control System, or IFCS. This system, designed to enhance flight safety and performance, featured advanced adaptive control technologies capable of responding in real time to unexpected shifts in flight dynamics or aerodynamic properties. By employing sophisticated algorithms, the IFCES could autonomously recalibrate its control mechanisms to sustain stability and manageability, even in the event of damage or system failures that altered the aircraft's behavior. This period of NASA's research and experimentation with the F-15 STOL MTD contributed valuable data and insights into the potential applications of these technologies in both military and civilian aerospace contexts. The F-15 STOL MTD program played a key role in advancing aerospace technology. Its legacy is evident in how it influenced the design and development of future aircraft by proving the viability and benefits of several innovative technologies, and nowhere more so than in fifth-generation fighter planes. One example is the Lockheed Martin F-22 Raptor, first flown in 1997. Inspired by the STOL MTD, the Raptor uses two D-thrust vectoring nozzles, allowing for exceptional agility and enabling it to perform stunts such as the Herbst maneuver or Pugachev's Cobra. Furthermore, the F-15 STOL MTD's exploration of supermaneuverability enhanced agility through advanced aerodynamics and flight control technologies paved the way for the F-22's superior performance in air-to-air combat situations. Another case is the Lockheed Martin F-35 Lightning II. While it does not use thrust vectoring in the same way as the F-22, the program benefited from the STOL MTD's developments in integrated avionics and flight control systems. The F-35's design incorporates highly advanced systems that provide the pilot with unparalleled situational awareness and control, concepts that were advanced during the STOL MTD's development. The F-35B variant's short takeoff and vertical landing capabilities can also trace conceptual lineage back to the STOL research and experiments conducted with the F-15 STOL MTD. Although the technologies are not directly transferred, the fundamental research into short takeoff and landing, as well as managing complex airflow and control issues at low speeds, contributed valuable knowledge that influenced the F-35B's unique propulsion system and lift fan design. Outside the realm of fighter planes, the advanced control technologies tested on the F-15 STOL MTD have also influenced the design of unmanned aerial vehicles, where stability control and autonomous operation are critical. While the direct impact on civil aviation is less pronounced, the technologies developed and tested in programs like the STOL MTD have also trickled down to improve the efficiency, safety, and operational capabilities of commercial aircraft, particularly in advanced flight control systems and aerodynamics.